Hi, Professor. This is Anush Kapoor. We are a part of Team 7. Our project name is Synthra.
Hello, I'm Bondi.
Hello, this is Poway Su. So basically, in this project, we're aiming to create a programming language that bridge the gap between interactive and declarative programming paradigm, providing a robust platform to explore the intricacies of system design, including parser, compiler, and runtime environment. This language, inspired by the familiar C-like syntax, introduce a unique blend of imperative construct and declarative feature derived from Prolog, enabling a seamless integration of procedure logic with advanced query capability by incorporating these paradigms. The language empowered the developer to write efficient algorithm while leveraging declarative rules for pattern matching, logic influence, and data querying. Okay, so the language grammar is carefully designed to balance simplicity and expressiveness, making it both beginner-friendly and powerful for advanced use case. It aims to serve as an educational tool for understanding fundamental concepts in programming language design, such as lexical analysis, syntax parsing, and code generation, while also offering practical application in problem solving and logic-driven tasks. This duality of purpose, educational and functional, makes the language an innovative contribution to programming landscape. Additionally, the project will explore the implementation of a runtime environment capable of managing imperative constructs like loops, conditionals, and variable assignment, alongside declarative construct for defining and querying logic relationship. This approach not only depends the understanding of hybrid paradigm, but also forced the development of novel programming technique that leverage the strength of both paradigms. Okay.
Okay, let's start with the grammar for the programming language then. Um, for the grammar of a programming language is constructed of multiple segments. It starts off with the whole program, and the program consists of function lists followed by a period. Uh, this segment here represents our grammar. The function list then is a function followed by more function lists. So uh, basically chaining multiple functions all together. A function then becomes a function name and followed by a block. So function definition followed by a block. Similarly, we define the predicate list, the definition lists, and the blocks as well. Our language supports assignment to expression, boolean, as well as string. And it has some general commands such as if then else, ternary operations, while loops, and for loops with in range flavor. It also has the declarative rules. These rules basically add to a database, knowledge database, and it can run queries against that database at compile time. Um, when we are interpreting the language, it supports printing uh, values from variables, printing numbers or expressions, and then printing strings. Uh, any command line can also be a block. So basically, then if then else will have multiple blocks, and a query has a similar syntax to what we see in Prolog as well, but it's a bit different. We'll go over that when we go through the examples. Our programming language also make sure that the precedence of operators as well as the uh, associativity of operators is met correctly. And yeah, that's it for the grammar rule. This grammar has been implemented using DCG in Prolog.
Okay, so I will introduce the tokenizer part. And what the tokenizer is implemented in Prolog as a model to transform the input strings into tokenized list. So which serves as a foundation for parsing and the further analyzing for all the input we make. So it processes the input stream by converting it into characters and identify tokens to be used. Let's go to the next page. This is how it works. And you can see the scan part. It scans the input and broke it into one piece by piece, identify tokens or characters. And if we go to the next page, here is a sample run for the tokenizer example. We can see the program outcome is the input we show in the first part, which is what we usually use in the daily life. And our tokenizer will translate into the tokens. Like first we start with definition, the mine, and blah blah blah. So all the program atom will be broken into one piece by piece the tokens, and then we go to the phase tree. So the parser tree will read it. And here goes introduce our parser part. The parser is like implemented in Prolog and designed as a model with a DCG. That's what we use for that. It interprets the tokenized input into structured parser tree. So the program syntax structure will read it. The parser includes support for the functions, expressions, and Boolean logic through table predicts for the efficiency. And if we go to the example part, so we still use the same example. Can we go to the upper page? The second part, yes. We can see how the tokens be transformed into the parser tree. And we go to the next page, how is a parser tree should be, looks like this. And you can see we break it into the trees to make it easier to understanding for each part of the sample. And if we go to the next page, it will be, yes, how the machine looks it like. And then we go to we trans the parser tree to the semantics. Please.
So the semantics module is all basically implemented in Prolog as well. It's gonna evaluate the parse tree with all the syntactic structures that it has and give meaning to each and every part of the syntactic structure, basically. And it'll also execute the program logic at the same time. So it in turn becomes an interpreter. In the semantics interpreter handles the functionality for handling variables as well as function environments, ensuring that the variable declarations and updates and lookups are managed efficiently. And if at any time there is a failure in the lookup, the program will stop. Function definition and rules are handled separately. The rule definitions are in turn stored in a Prolog file that the rule query runs on, and the functions are stored in a function environment. The outputs of the Prolog rules are stored to a file and then updated in the environment if the query in turn was successful. So here we saw, this is the same example again. This was our parse tree, and in the program, we are printing one of the two things. If A is greater than B, we end up printing here the product, which is also gonna be 2. So this is what is being printed on the screen. The tokens and the parse tree and all of the other printing is just for our demonstration purpose over here. After the language runs, the only 2 would be printed otherwise. Yeah, so let's go over the language mechanics for a bit. The language has an environment. This environment is basically a list of 2 environments. One of the environments is a variable environment, and the other is a function environment. The function environment stores all the function definitions, as well as the declarations, as well as the definition lists that are being passed when a function is defined, and the body of the function as well. When a function is called, we generate a new environment, which is the local environment, and take any of the parameters that were passed to the function and put them into the new environment, into the new environment for the function call. And then that function is called with the local environment. The language also supports built-in Prolog reasoning. So if we write a Prolog predicate, which is a simple, for our example purpose, we have used a simple one, such as a parent predicate. It can reason over that and search for the correct response from that. We have also tested it for the most of the imperative features such as loops and conditions as well. The use case for this language was another part that we were looking into. This is a language that is combining both imperative and declarative paradigms. So some sort of a feature where we can use this language would be if a problem is easier to conceptualize if it is expressed recursively by transversing over the output iteratively. So we can basically gain more control over the execution flow. And if there are some decisions that are made, we can potentially pause, resume, or even modify our recursion if from the iterative calls. Because it will make the visualization easier, the debugging process will also become easier because recursion is many times harder to debug than normal iterative code. Uh, the use case for this can be something like a game AI that has multiple decision trees made at each step. So if we are iterating over all of the game turns and then recursively exploring the predicates to look ahead basically in the game possibilities, then we can use something like this. It'll be useful for look ahead that is implemented in many games nowadays. And similarly, for the same reason, it can work for tactical games as well. Over to you, Albert.
Okay, so I will make the conclusion of like this part. So in conclusion, our system integrates three essential components, which is like tokenizer, parser, and semantics model, forming a cohesive Prolog-based pipeline for interpreting programs and use main.prolog to integrate them. The tokenizer eventually converts input string into tokens. The parser organizes these tokens into structured parse tree, and the semantics module evaluates the parse tree to execute the program's logic. Together, this module create a robust foundation for developing Prolog-based compilers or interpreters, ensuring a seamless transition from raw input to program execution.
Yeah, that was it for our
That was
presentation.
it. Yeah.
Let's look at the GitHub again. We have mentioned the build steps here, how to run the program. Um, just make sure that all the files are in the same folder. If they are in the same directory, you will be able to run them using the command as shown here in the example as well. We have added some sample programs over to the data directory. This is one of them that shows addition, product, division, and difference, and the print part. This one showcases the conditional statements. There is one, this is just another test one that we created. It just writes a Prolog query to another file, and then it's not really querying in this one. Then our for loop, while loop, and then this becomes our Prolog, similar to Prolog rule structure. It's just followed by a rule keyword, and then each query, if it is a query that's not using a variable, rather passing a reference that it wants a value, it's followed by a question mark. If the question mark was not here, it'll try to fetch the value of x and then pass that value there as the query call. Yeah, that's the data. And then the docs folder also has the documentation for our programming language. Yeah. I think we can just go to our demonstration now. Yeah, so from the source directory, we can just run a program which is swipl-f, and then the file name, and ask it to run, and then give the file name that you want to run. Here we are running 5.7. Let's look at 6.7, which is giving us 3. 6.7, if you see the code over here, it's basically asking who is the parent of 4, which will be 3 from our database. This is the database it creates for the program. Yeah.
Yeah.
I think we can
Yeah.
wrap it up.
I think that's it. Thank you
Okay.
for watching.
Yeah.
Thanks for listening. Thank you.